Hi, I'm Joe Garner, and this is a tour of the Bristol Cybersecurity Group Industrial Control System testbed and a demonstration of an attack against a converged ICS and Industrial Internet of Things environment. So briefly to explain who I am an RA in the Bristol Cybersecurity Group. My full job title is Research Associate in Experimental Infrastructure for the Security of Cyber-Physical Systems, and in basic terms that means I run the cyber-physical systems and ICS testbeds and do ICS and IoT security research. My primary interests are in vulnerability discovery and finding new ways to attack devices. I'm also a lecturer and co-lead on the Resilient Infrastructures unit of the TIPS at Scale CDT, and I'm the founder and current leader of the Bristol Ethical Hackers Ethical Hacking Group. So before we go and look at the testbed, we're just going to cover what we actually do on this testbed and what our motivation was behind building this. And there are 5 main use cases of research that we considered when building this testbed of what we wanted to do. The first of these is to look at issues of convergence between your information technology, IT, and your operational technology, OT, spaces, especially where the Internet of Things and the industrial Internet of Things are blurring these boundaries. So traditionally, your IT and your OT environments were very, very separated, but now these lines are being blurred. We're to perform security analysis of industrial control systems and industrial Internet of Things devices, and also the top-end software environments behind them. We're to look at intrusion detection within converged IT and OT networks. And there's a lack of data sets available for industrial control system security for researchers to use, so we want to be able to generate data sets and release them out of both baseline normal operation of these environments and also compromised environments as well. And finally, we want to look at the human factors side of things. So how does this impact upon the safe and secure operation of IT and OT environments? For example, how do your OT engineers operate while under pressure when they're being attacked? And to support these 5 areas of research, we had 5 design and build principles that were followed when we built the testbed and designed it. The first of these is we have diversity of both devices and software. We have multiple manufacturers and both legacy and non-legacy devices, so we can cover all bases of different types of deployment you may have out there of the latest, greatest devices, but also much older devices which have a lot poor security. We have scalability support for increased device deployment and at a reduced cost, so we can very easily expand the testbed by linking up to other testbeds or deploying new field sites. And we can also expand on this by simulating and virtualizing as well. As it's been used for researchers, we made effort to reduce the complexity for deploying devices and software to the testbed and also for maintaining. So when a researcher academic comes and uses the testbed, especially an external partner, they can do this very easily without having to do lots and lots of learning and preparation beforehand. To support our dataset generation, the data capture should be optimized to enable appropriate capture at any and all points of the testbed. So as you'll see a little bit later, we have lots and lots of data capture availability on the network of the testbed, so we can build those datasets from that. And finally, and most importantly, as we do have lots and lots of physical devices here and electrical devices here, the safety for the researchers and technicians working on this is paramount at all times, and the testbed is designed to support that safety. So now we go on to the Bristol Cybersecurity Group testbed. This was built to a published reference architecture for security ICS testbeds. We have multiple physical and virtual industrial processes, each within distinct centrally managed field sites. We have an OT vendor agnostic design with control equipment from multiple manufacturers. We have a realistic corporate OT and IT network environment and a real-world top-end software-based security operations center. So we now start with our first physical process, which is our water treatment plant. This is an off-the-shelf Gunt CE581. This is a water treatment plant that sits on a small scale and is sold to trained water treatment engineers. So if you put dirty water into this and you put the right chemicals and test the water correctly, you will get clean drinking water out the other end. We don't do that, we just run it in a loop with tap water because it's a lot easier that way. This is a 3-stage filtration, absorption and ion exchange process. There are 3 stacks of tanks and each one of those is 1 stage. This largely comes as standard, but we did ask the manufacturer to make a few modifications for us, which I'll show in a bit more detail in a second, but all of these are a removable pipe to allow easy sensor installation and also some pressure release valves for safety. This came with a control cabinet which came with a PLC and a HMI screen. We swapped these out to replace them with our own control architecture which sits inside a separate room, and I'll show you that shortly as well. This is a more full view of the water treatment plant. So you can see we have the 3 stages of filtration, which is gravel and sand, absorption, which is aluminium oxide and activated carbon, and ion exchange, which is a magical process I do not understand personally. And these 3 times, and the water flows for each one in turn, through this one first, and then through this one, and down for the third one. But you can do just one stage, or 1 or 2 versus the second stage, or 3 stages. You can set that with the program. On the left here we have our 2 water tanks. The right one is for dirty water, where the pump sits, and the left one is for clean. In reality, we just run these in a loop. In the middle here we have our removable copper pipe. So it's usually just a plastic pipe that goes straight up. We had this copper pipe added in here with a valve at either end. So if we want to install a new sensor into here, we just have to close the 2 valves, remove that pipe and drain that pipe, which is a very small amount of water, and then we can install a new pipe there with any sensors we wanted added to that. And over on the right here we have the original control cabinet. These bunch of grey cables that go out of here and out through the top, these are our replacement cables where all the wiring side of there now goes out through those to our control cabinet in our second room rather than the PLC in there. And the built-in HMI is in place of our wireless Siemens HMI up here. And then for safety we have 2 main parts, well 3 main parts. We have the pressure release valves which sit on top up here, which you can't really see behind this bar. So if we do override the pump, the system pressure doesn't go to any dangerous levels, the water will be let out back into the tanks. We have the overflow buttons down here, so if the water leaks, any part of it, any tap is opened, there's catch water. This does sit inside our kitchen, so it will not flood our office. And also, there are some moisture sensors that sit in each side of each of these 3 tanks, and a safety cut-off system built on Arduino in here, so if they detect water in those tanks, it will shut the power off to the pump. Our second physical process is our factory. This is from a company called Fisher Technic. This is currently under construction. We are largely have this program now, but there's still some bugs we're trying to work out. This is a multi-stage manufacturing process. So we have a warehouse, a robot arm, an oven and sorting, which is on here. And this is, even though it's a small scale, it's a much more complex process than the water plant. The water plant has 4 valves and a pump, and that's about it really for outputs, and then a few temperature sensors and pressure sensors. Whereas this has about 70 or 80 different actuators and sensors and so on. It's a much more complex process. It requires multiple PLCs to make it run, so we can look at a much more complicated process and how the processes interact, and attack on one, how that affects the other ones here. And finally, we do use a virtual process, mainly for teaching and prototyping, and this is called Factory.io. It's from a company called Real Games. This is a fully virtual process where you can build up a manufacturing plant and connect this directly up to PLCs. You can build quite a large scale process in this, a complex process, without actually having to build anything or wiring up. For Siemens and Andy Bradley devices, you can connect these over Ethernet. You don't have to wire up the processes. It can also talk to Modbus based devices, but for third-party PLCs that aren't supported, you can buy hardware interfaces for wiring them up to real PLCs. As part of this, we can also inject faults into the inputs and outputs of the software. So if we want to make one part go wrong, we can do that in there, and that's supported by the software itself. And you can see on the little demo video there on the right, this is a very simple process we use in our teaching quite often. The program on the left that's reacted to that, and the configuration for that at the top as well. So this is an example of one of our field site control boards. So as I mentioned when we were looking at the water plant, we replaced that control cabinet that came with it with our own control board that's in a room, and this is the control board for that water plant. We have 3 of these that we have built, and these are all built to a reference standard with the same terminal configuration and the zoning for all our 3 processes. This has flexible capacity for multiple devices, so all devices are mounted onto these mounting plates, and we can easily unscrew these and pull the whole device off with the wire looms that connect up to the terminals near the top. And all the wiring has to be done within that small local area, rather than having to wire it to a separate room where the water plant sits. For safety, all the 240 volt main supply is confined to this lockable box towards the bottom, and then it means all the power that's on this board is 24 volt DC, which is relatively safe for a human to go and be near. This does sit inside a locked room. We have onboard data comms for screen these configurations, so we have an additional switch down here. This is a checkpoint firewall, and this is a wireless access point for our wireless HMI. These are real world devices down here, so we have both new devices. This is the latest greatest Siemens SM1500 PLC, and this is a legacy Siemens ET200S PLC. This model is a few years old, this model is about 20 years old. And this is what it actually looks like in that room. We have a full wall of 3 of these. So the one on the right is one you saw in that previous photo. This is the water plant. The one in the middle, which is a bit messy wiring at the moment, but it's being tidied up, is the control board for our model factory. And the third board over here is for a future preferred process that we're currently in the design stage of, but it's currently being used as a sandbox for devices. In terms of control devices, we have devices from multiple manufacturers, both legacy and new devices. These include programmable logic controllers, human machine interfaces, remote telemetry units, industrial network switches, wireless communication devices, wireless sensors, security appliances, and so on. And these are an example of most of the manufacturers that we cover. So the 2 biggest players in the market for us are Siemens and Anibali, but we also have devices from ABB, Honeywell, Delta, Westermo, Yokogawa, Checkpoint, Schneider, and so on. To support the backend of the testbed, we have a complex network environment. Our testbed network is fully isolated. There is no connection to the wider university network. It allows us to keep the network clean and ensure that it can't be attacked from outside, and any attacks that we do in the testbed stay within that testbed. The network is fully realised with physical Cisco switches and routers, but all of the physical networks are represented by VLANs, virtual LANs within the testbed, so we can map our virtual machines to them. The only external access is via the private VPN, or for a 4G connection to our remote field site, which we'll see shortly. There is a network tab on every subnet, all the orange cables you can see in the video on the right, and we are currently building an SDN twin of the network infrastructure for software-defined networking to allow us to look at programmable networks in industrial control systems environments. And you'll see that testbed down at the bottom right. And this is a map of our core testbed network infrastructure. And you see here the network is formed of 3 components. We have the experimental network, which is there for researcher access. So we have the management network, which allows you to go and connect to different virtual machines on the network, and the spanning network, which is there for data capture, and that's all those orange cables. We then have the IT testbed, which is currently not very populated with services, but is there to emulate a corporate IT network. And then we have our OT testbed, and the key here are the 4 field sites. Field sites 1, 2, and 3. Field site 1 is the water plant, field site 2 is the factory, field site 3 is currently at the sandbox, and we have the mobile site, which are mobile demo box, which comes in over 4G. This is a fully realised network. We can put devices onto these. We can install software into the utility network and the demilitarised zone and so on, and test how the software performs in these networks and control access around as you would if you had a real physical network in there. We operate all our services in a fully virtual environment. All our services and software is hosted on virtual machines using VMware vSphere. And all of the VLANs represent each of our different subnets in our network are mapped to our virtualization server. And that is in this rack down here at the bottom. When we deploy a VM, we can very easily then map this to VLANs and add it to any subnets in this network, in that environment. This allows for very easy deployment, and also all our VMs are connected to our management network, which allows for easy access and maintenance. For remote access, we have a dedicated VPN. This allows remote access to all our services from off-site, and also the testbed allows for field sites to be linked to an external top end, and vice versa. So our individual field site represents one process. We can link those to a different testbed if we wanted to test somebody else's backend, or if somebody else has a field site, they can link it into our backend and use our software, and so on. And this is there to support both expansion of the testbed and also collaboration with other testbeds. So the main control center of our testbed is our Security Operations Center, or our SOC. This is a 3-station SOC within our lab. This is situated on our SOC network, and all of our 3 workstations here are physically connected to our testbed network. There are 3 Ethernet cables that go from this room back in through the ceiling into our server rack in the other room. We also have a small switch in here that's configured with easy physical access to the other VLANs. There's 5 or 6 different VLANs mapped onto there, so if you want to plug one of our lab maintenance laptops into here, we can do that in there as well safely. The 2 primary use cases for this room are both for controlling and maintaining the testbed, and also for using human-based studies. So from this we can access any VM, bring them up on the screens via RDP, and then we can either use it for maintenance or for doing studies, such as putting a person in front of the screen, attacking the testbed, showing them the outputs and seeing how they react under pressure. And this is the full lab room, so the SOC is also combined with a sort of lab type room, and it's been modelled here by Manolis, who's one of our second year PhDs. And you can see in here we have the SOC on the right, we have our training bench over on the back left side, storage for our devices, and some workspace for doing experiments and working on devices here as well. We then have our convergency and dependency testbed, and this consists of a built-in management system. So again, this sits in our coffee room near the water plant, and this is a built-in management system that features the latest and greatest trend controller. There's also a remote site to this, second site, which is inside our server room, which also features the most widely deployed built-in management controller in the UK, also made by Trend. This is here because we can plug in consumer-grade IoT devices into this, so things like Philips Hue, smart locks, and see how they interact with the BMS system. This is a very similar system to what we get in industrial control systems, and also when you have a plant that has physical processes, your ICS in there, there will also be a BMS system in that building, which can control things like the lighting, the heating, the ventilation, even things like the fire detection system. These all do interact, even if they may not be physically connected. So we can look at the issues of convergency and also the dependency of these systems on each other in there. So we now come on to our remote field site / demo box. This is a small self-contained process of sorting conveyor belt and the control systems for this that we can either run as an isolated demo environment, but also we can link it over to our testbed as a remote field site over a 4G connection. This comes in two petty cases. The first is a control one. In the lid of it we have a HMI screen and a 4G radio. The 4G is what gives us that connection back to our testbed, and there's a dedicated line into that. And then in the bottom of that case we have our control system. So we have a Siemens 1200 PLC, a 200 PLC, and a Schneider telemetry unit with a small Western mode physical switch inside. And then over here we have our second box, which is the physical process. These link up with just with Ethernet cables. The entire demo setup is two petty cases and a laptop bag to take some laptops to run some of the software. We can run this via the BCSG top-end environment of our testbed. Generally when we run demos we run it on two laptops doing the same software, but just doesn't rely on that 4G, because when you get into a conference center then you cannot rely on a 4G connection working with lots of people. So we do run this as a demo. We've taken to lots of events. I'll show you some pictures of those in a second. But we also use this for also smaller scale projects as well. So a lot of the time when we have final year undergraduate students doing projects, they will come and use this as a test case for that, because it's small scale, it's relatively cheap compared to the main water plant and the control boards, and it's a much simpler little process to go and manage. So this is just showing the remote field site, and this is when we first showed it off at Cyber UK event back in 2019. And we showed this on stage up in Glasgow. We took them up there and attacked this live on stage. The same attack I'm going to be showing you shortly. As well as the big events at Cyber UK, we also take the demo boxes to smaller events like the B-Sides conferences that happen around the UK. On the left there we are at B-Sides Wales in Cardiff, and on the right there B-Sides Bristol that held at UWE a couple of years ago. We run this at a smaller scale so people can come up to the table and we run the attack for them on demand there. Most of the people, they're all security experts, but they have never seen any of this stuff in real life before, and it's very nice seeing them see how this actually operates in real life on there. As you can probably tell from what you've seen so far, the test bed is quite complex and also quite expensive. So to support this, you have multiple levels of training and prototyping equipment available before you go and touch that main test bed. We have our ICS teaching boxes, we have our training bench, and we also have the remote field site you just saw as well. There are many benefits to this. One is they're a lot lower cost, there's a much smaller learning curve, and also there's a lot less risk of flooding the office. The first and primary stage of our training infrastructure is our ICS teaching boxes. We have 18 of these total, 12 of these for Siemens devices and 6 of these for Allen Bradley devices. These are fully designed and built in-house by me and our electrical engineering team in the engineering department. We use these primarily in teaching on the CDT course in the Resilient Infrastructure Unit. We also take these to certain events, so at the beginning of 2020 we took these up to Newcastle for PhD Winter School, where we ran a 3-hour workshop with people to go and learn how to scan these and attack these systems. And we also do these in some student projects as well, so final year students for undergraduate can come and use these for projects as well. These are primarily designed to work with factory I/O, but they all do also have the physical I/O mapped on them, so we can go wire some devices into these as well. You see how that operates there in our CDT room, being modded by Suyi, who's one of our second year students now. We now come on to our training bench area within our SOC room. This is an area where we have two small-scale physical processes from a company called Eldro Create. Both of these are conveyor based. One is the same conveyor belt we have in our remote field site box, and the other is a much more complex manufacturing sorting process that you can see in the video on the bottom right there. This also comes with a desktop with all the configuration software you need, and also some training courses for learning things like ladder logic, which is the language primarily used for programming these sort of devices. So you can go and sit here and learn how to use these, learn how to use the software, but also we can use these for prototyping projects as well before we go and move them onto the main testbed. This is fully isolated from the main testbed, so there's no risk of damaging the testbed network or no testbed devices. These are relatively cheap compared to most of the equipment we have around the lab. As you can tell from all the slides you've seen, we have a very large-scale physical testbed here. We have lots of physical processes that need maintaining, and also have lots of electrical devices that we need to wire up and so on. A lot of this does require expertise, specialist expertise, so we do fund a full-time engineer in the electrical engineering workshop who can perform building and maintenance tasks for us. I can confirm that I should not be allowed to wire things up if you want them to stay wired in for a long time. The engineers also help with health and safety, so they do proper testing for devices, electrical safety testing, and so on. And we also do have an on-site workshop for prototyping repairs, so this includes things like a MakerBot 3D printer and a circuit board printer. And you can see that in a bit more scale here, where we have the full workshop lab. So we have a HP Spark PC with comes with a 3D scanner, our MakerBot over there, and this is our workshop bench with a soldering station and tool bench as well. So we can do all our maintenance inside our lab. And now we come on to our demonstration part of this presentation. This is a demonstration attack against a converged ICS and industrial IoT environment. This was originally shown as part of the Petrus demonstrator project that we completed back in 2019. And it's the same demo that we showed at Cyber UK on stage. So before we begin, this is shown on our remote field site. We would usually show this against the water treatment plant, but unfortunately we do not have access to that easily enough at the moment. This demo features pre-recorded footage alongside updated screen captures that have been edited together to appear as they would on a live demo. So this is an example of a typical converged ICS and industrial IoT environment. On the left, we have our ICS and IoT OT network. So here we have our ICS devices, our PLCs, R2s and HMIs. We have our industrial Internet of Things devices, which use protocols such as wireless HART and LoRa. These are things such as thermometers, gas sensors, flow sensors, and so on. And then we have our IoT devices, our more consumer style type devices, so things like smart sockets, temperature sensors, smart lighting, and so on. We then have our ICS and IoT supervision network. So this is our SCADA software, such as ClearSCADA, and things like data aggregators and historians, such as Kepware, which can collect data from devices and store them or send them out to other programs for processing. And then we have our industrial IoT cloud platform. This is things like Wonderware for data analysis, and also ThingWorx as well. So the target environment we're going to look at today is our mobile testbed remote field site. So as I mentioned before, this is a sorting conveyor physical process, and you can see that operating on the right. There are 3 differently sized metal blocks, a small, medium and large. The process measures them and pushes them out to 1 of 3 buckets on there. This is Siemens Schneider control equipment, so we have a Siemens S7-1200, which is the main brains behind the process. We also have an ET200S PLC in there. This isn't actually used in controlling the process, but it is live, and we do attack this as part of the demonstration. We have the Schneider SCADA Pack 32 telemetry unit, and a Westermo industrial switch for communications. Up in the top, we have a Siemens KTP1200 HMI screen, and that is what displays the system state to the operator locally on there. We also use 2 laptops for our compute resource, one for our ICS supervision network and one for our cloud environment. All the attacks are carried out using a Python wrapper script, so it's mostly just Python code around some publicly available libraries, but no, we can't share this. There is one exploit in there that isn't public yet. This is a close-up of how that looks. So put the large block onto there. It gets measured by the sensors over here. And push it into the first bucket. When I put a medium-sized block onto here now, it'll get pushed into the second bucket, and then the little gets pushed off into the third bucket. This is what this looks like on that HMI screen. So when I put the large block on, you can see the pusher is pushed and the counters increase with each size block that goes off onto there. This is currently running in auto mode, so that means that it does all the processing. You see up here. If we put this into maintenance mode, it's fully manual control, so you have to start and stop the conveyor and push the pushers manually. So for our demonstration environment, this is how we cut down that original diagram. For our ICS OT network, we have our two PLCs, our SCADA pack temperature unit, and our HMI, which sit inside that control box and connect out to that physical process. On our first laptop, our ICS and our IIoT supervision network, for telemetry we have ClearSCADA, which talks to the SCADA pack 32 RTU, and we have our data aggregator Kepware, or Kep Server EX, which talks to those two PLCs and pulls data off them directly. On laptop 2, which is our cloud platform, we have ThingWorx, which is our data analysis software. That has a direct connection down to Kepware. Kepware sends data up to ThingWorx, and then ThingWorx displays it on the screen. To show these in more detail, so ClearSCADA is from Schneider Electric. This is designed to run locally, and it displays data physical processes. We have a very basic display here that just shows the state of the Modbus connection, and if the process is running in auto mode or manual mode. In reality, you could populate this with a much more complex display, showing more of the state of the process. This talks to the SCADA pack 32 over Modbus protocol. In this case, when the auto changes to off, as you can see in that video, that is treated as alarm. The alarm is raised, and you have to go and clear that alarm to continue. And when it's put back into auto mode, that will change back to on again. Kep Server EX from Kepware is our data historian. Again, this one's locally. This is designed to sit inside an individual field site. And this is granted direct access down through the firewalls to our Siemens S7200 and E200 PLCs, and is reading memory addresses from them to read individual variables of the devices. So probably here it's reading the counts of each blocks and the auto mode states for them to go and send that off to ThingWorx. It's reading from the device at about a 1 second interval, so about once every second it'll read from the device, and then also once every second it'll push it over to ThingWorx on there over a HTTP connection, not HTTPS by default. We then have ThingWorx, which is from PTC, who are now owned by Kepware. This is a cloud industrial IoT platform. This runs on Ubuntu using Tomcat. We were doing a pre-built VM with Ubuntu 18.04 running Tomcat 8.5 and just given the password and said, this is how you go and start the program. This receives the data from Kep Server EX about once every second and displays the data on screen via these mashups. You can see an example of this one here for the data box where you have the 3 counters and auto state. And as counters go over the conveyor belt, it reads it off the devices from Kepware and then it updates the screen on there. So on to our attack objectives. The first is we're going to compromise the IoT cloud platform, which is ThingWorx. We're going to create a network environment for staging our attack. And they're going to do some network and ICS reconnaissance. We're going to mask the attack from the various operators on the planet, and then we're going to make the process go wrong. So the first step of this is to compromise our cloud platform. We're going to assume that the ThingWorx VM has already been compromised due to its reliance upon the Tomcat server. So Tomcat 8.5, if you go and look up for vulnerabilities for this, this is the first page of results that you get. So you have 2 critical, 10 high, 8 medium, and there are some low impact vulnerabilities as well. It's very easy to go and compromise the machine via Tomcat 8.5. So we assume we've already compromised the machine and we've loaded our task script onto that machine, ready to go and use directly. So the next stage is to go and create our network environment. So there's quite a few steps here. The first of these is we're going to terminate ThingWorx and start a HTTP listener. So it's very simple. This is our task script running on the right on the ThingWorx VM. So we terminate ThingWorx. We essentially kill the Tomcat process. ThingWorx no longer receives data, so that mashup has gone blank. And if we go and look at Kepware now, once we kill that process, then Kepware is going to start throwing errors because it can no longer communicate to ThingWorx. On the right there, we just have a Wireshark live view of the packets going from Kepware to ThingWorx. And you see when ThingWorx goes offline, we start getting lots of failed packet deliveries coming up there. And this is where somebody starts to panic because now Kepware is no longer working, Firmware is no longer reading data. So now on the firmware side, we set up our HTTP listener, and then on the Kepware machine, our engineer is going to go and open the Kepware manual, and that manual is an embedded exploit, which is going to set up a HTTP connection back out to our server, to the firmware machine, but it's now going to connect to our listener, and then we can set up a HTTP session between the Kepware machine and the firmware machine that we control, and then we can start using that as a proxy to route all our traffic from our attack script out for the Kepware machine. So if we go to the bottom right on the firmware stream, we start the listener. This is just using Metasploit's built-in listener. So that's now printing the requests coming from Kepware, because it's now seeing them but it's just ignoring them. Kepware is still not actually going to work. So the operator goes and opens a manual of the desktop, which we've put there. There are some problems they have to get through, but they're desperate because the factory isn't working right. And now they can go and view that manual. But as I said, as this is a compromised PDF file, that's now opened up a connection. You can see it down in our bottom right down here. There's now a connection set up. We set that into the background, and then we relaunch our attack script using the proxy going through that HTTP connection. To the operator on the Kepware machine, it doesn't look like anything's happened, but in reality now all our traffic from Frameworks is now going to go out through the Kepware machine and is allowed by all the firewalls. So now we can start doing more of the actual attacking part, and to start this, as with any attack process, we need to do some reconnaissance. We're going to start by doing some generic network reconnaissance to find the devices that are there, and then we're going to do some more specific ICS focused reconnaissance to find out which specific devices exist and what they're doing. So first off, we went an Nmap scan. We have heavily cut this down to only look at certain IP addresses and a few ports in each, otherwise it would take a very long time. So as you can see, this is running through. Most of these come back denied, but there will be a few that come back as okay, whether it is a valid connection there. So as you can see now, we have 4 devices that are alive: 172.24.9.99.100.101 and 200. 99, 100 and 101, which are these 3. These all have port 102 open, which is labelled as ISO TSAP. Port 102 is the standard protocol used by Siemens for their S7 protocol, so I can give you an idea that all of these are Siemens-based devices. The bottom device has port 102 closed, but has port 502 MBAP open. Port 502 is the common port for Modbus, and that indicates that's a Modbus device down there. In fact, that is a SCADA pack in this example. So now we know which devices exist, we can go and probe some of these a bit more precisely. So we know that port 102 is for Siemens, so now we can go and run some certain scripts to look at these devices for scanning Siemens devices. The first of these is the S7 info script you can find on GitHub. This is specifically designed for reading off device information from Siemens devices that have S7 ports open, because the S7 protocol lets you freely read the memory addresses where these information sits, and you can fetch that information to look at. The 2 most important ones here are the first number here, which is 60S7. That's the Siemens product code, so every Siemens device, down from a PLC down to an individual I/O port, has a Siemens product code. 60S7 means it's a Siemens S7 device. So that tells you what hardware it is. This is the Siemens ET200S here, and also we have the firmware version. If you know the hardware and firmware version, you can then go and start finding exploits for this device. Unfortunately, that script no longer works on the newer Siemens devices, but we do have a built-in script now in Nmap, which does exactly the same thing for the newer devices like the 1200, and again we get the module code and the hardware software version come out through this. So here we have a Siemens 1200 software version 4.2.3. Finally, we now know what the devices are. We could go and exploit these now, but we want to go and figure out exactly what they're doing because we want to do a bit more advanced attack. So we need to get a copy of the logic that runs the process off them. For the 200S, it's very easy. It gives us free read access to that area of memory. So via the protocol, we can just set a command to read off one data block, one function block from that device. And then we have to go and manually reverse engineer that, which literally takes a second. For the newer devices, that no longer works. But if you have the Siemens TIA Portal software for configuring them, that gives you the functionality to actually go and recover logic from a device, and it will actually parse out for you, so you can go do that to work out what's going on as well. So now we know what exists in the network, we can now go and actually perform our attack. And this is stages 4 and 5 of masking our attack and manipulating the process. We're going to do it at the same time because they use the same technique for them. So the first what we're going to do is we're going to bind ourselves from the operator sitting in the control center who are looking at clear SCADA that's talking down to that SCADA pack. And we're going to do this by taking the RTU offline. So you can see here that the SCADA pack is currently running. It's running healthy and the auto set is on. And we run our exploit against this. This is an actual exploit vulnerability. This is a replay attack that changes the IP address of the device. This is a public bit of code yet, so I can't tell you exactly how it does it, but it is a audio replay. So now we change IP of that. We basically switch IP address from .200.201. ClearSCADA does have quite a long delay. It's about every 15 seconds it reads my device, but you'll see soon that healthy motor drop will change to failed, and the auto run will change to pink because it no longer has a connection down. So now the operation center can no longer see what's happening down at the process through ClearSCADA. We're now going to both mask the attack from the people sat locally in the plant who can see that HMI screen, and also make the process go wrong. So what we're going to do is write down to the device. The Siemens S7 protocol lets us freely write memory addresses as we want to, and if we appear to do that fast enough, we can overwrite memory before the device can, and change the state of outputs which interacts with the physical process. So we're going to freeze the HMI values on the PLC. The values that the HMI sees are going to stay the same. It's still going to show it if it is in auto mode. But in fact, what we're going to do is switch the whole process into maintenance mode and start the conveyor belt, which means that devices will run off the end rather than be sorted. So we start that running now, and you will see a pop-up come up. You can see lots and lots of packets being written repeatedly. And then now, when we go and put a block on the process, it's measured, and rather than being pushed off into the first packet like it should do, it's going to go and run off the end. And just a wider view here so you can see the HMI screen. So in the attack, I put the block onto the conveyor, and you can see that HMI screen is no longer updating. It's still showing auto mode even though we're now maintenance mode, and that block runs off the end. That's a very simple way to make it wrong. 2 years ago, we had a summer intern, and we asked him to go and try and find some more ways to make this go wrong using the same technique. And he found a few different ways a bit more interesting to make it go differently wrong. So the first of these is to make it missort a block. So usually the large block would go off the first bucket, but in this one you can make it go off into the third bucket. So now, often be sorted into bucket 1. The large block's going to be sorted into the bucket for the small blocks. The next one we can do is we can turn a pusher into a puller. So rather than push a block off, we can make it pull a block off by changing the timing of when the pusher extends and retracts. This was best on the middle-sized block, so we set it to use it on that one. So now when the middle-sized block goes down, the pusher will now pull that off the conveyor belt in the wrong direction. And finally, one of my favourite ones, we can make the whole thing go backwards. And for good measure, let's also cut a PLC. So the old ET200S device, these are vulnerable to a replay type attack, where you can remotely start and stop these PLCs using the Siemens software. You can replay that stop command to stop a device over the network. And put it in stop mode. When the device is in stop mode, it will no longer operate. So if you watch the two green lights, vertical green lights here, you'll see that when we run the attack, the bottom of these turn to orange. That device is now in stop mode. The only way to repair that is to go and flick that little switch on the PLC physically. There's no other way to put it back into run mode remotely when you do this replay attack on there. If this is a remote pumping station for water treatment or similar, you may have quite a long drive to go and find this device and flick that little switch to make it work. Thank you for listening.